calculator results of so again, before the first step we need to make results of so we know that LGL preserves compact object because the left adjoint always preserves compact object. We know already from yesterday that LGL exists. Hence LGL has to exist because it's left adjoint preserves compact. It's not a question about that.
If we know that the Langlands functor preserves
Say again?
If the Langlands functor preserves points.
No, we don't know that. We know that it admits the left adjoint. And theorem 1 talks about the left adjoint. So not theorem 1, but this assertion. We're talking about this. This function preserves left adjoint. Preserves compact object because any left adjoint preserves compact objects.
Left adjoint.
German.
Left adjoint.
Left adjoint that admits a continuous right adjoint preserves compact objects. We are in the world of functors that commute to the fullest. Anyways, so here we wrote the diagram, which is just the lower portion of fundamental diagram here, and by now let me just pass the left adjoints. I wrote left adjoints everywhere. I identified them. So left adjoint of CS is inverse. Left adjoint of coef pointer sheet. Left adjoint of T is scale. So now what are the left adjoints there? So left adjoint of J lower star J upper star. Left adjoint of gamma stack is one stack. So I wrote this diagram here. And let me just write the diagram of opposite functors. So here I wrote it. So now, as I'm repeating what I said before, everything is acting on the gravity check, run, and we'll see in a moment that, well, everything is compatible with actions. We'll see in a moment that these arrows go inside. And therefore, if you want to show that this one is going inside, it's enough to show that these arrows go inside. But again, because everything is in a situation with an action, and we are talking about arrows out of an acting agent, it's enough to show that the arrows go inside on the unit of that. So therefore, what we have to show is that you start with this diagram, and this diagram is source is that, so it really produces objects. We want to show that you can take on to obtain the same diagram. So like this opposite of objects are the same. So let's see what objects these are. So I evaluate this Poincare on the vacuum, so I get Poincare sheet back. And formally speaking, so this is what I have, but I rewrite it like this. So remember this LEU. So I restrict to U and then apply the left adjoint. So this, I want to be really pedantic. That's why I rewrite this as this. All right. So now, on the right hand side, this right arrow reduces to the structure sheet. So under tautological duality and quasi-code, the dual of the structure sheet is itself. So indeed, dual. So the opposite of the right arrow is the same. They're the same. But now let's see what happens to this left arrow. So I write my initial functor, my object like this. So it's like in this block. And what I should be writing like this, but if you recall the definition of how the self-duality of the Caspital category was set up, this EUL op is itself. So I rewrite this object like this, which is the same as the EL Poincare star. So hence I'm down to showing that EL Poincare sheet is Poincare star, and that was the special that we had. So this is how it's organized.
Shouldn't be one more right.
No. No, on the right here.
No, after Poincare.
You mean here?
Yes.
No, there I'm applying duality to the unit object, and it's unit in rep check the unit. The global unit is itself. So I punch the logic again. I repeat. This I create left the joint, then I calculate it's off. Calculate off, it's not going to start with the vacuum object. Calculate this object, and identify its dual is the same thing, but treat respect by star, and I say that they are indeed the same when you project, when you apply this L and E these two objects differ by something which is different. So that was my talk.
And what was precisely this domination statement?
Oh, it's something that appeared. Day one is that rep. You check run, it's functor log. You check spec. The polar quadricle boxes is in fact very quotient. Okay.
I will explain.
And this, yes, and Lynn will explain this as a side remark to what something that he really has to explain with his talk right after lunch. So that was needed in order to show that these, in fact, that these errors coincide, it's not shows that the recombinations coincide. That was the idea. All right, so okay, further questions,
There were also the line draw.
please.
One was the I strip and the I star, and the extensions of the other.
Yeah.
Vectors plus.
Yeah. Okay. It's more than I have the energy for right now. We'll do it. You and I involved. So I'm slightly tired of this. Like more about the sound.
Yeah, I was talking about factual compatibility.
Yeah.
Suppose is it related to the factual compatibility function?
We didn't have time to go for a sheet.
Yeah, I mean, so the relationship on the left hand side will come to the
So we have the following picture. Yes, we're talking about this diagram, right? That was the Stefan Poincaré functor. Yeah, that corresponded to its middle localization. So we're okay with that, right?
yeah, but I remember Sam yesterday introduced the factual combination to be the
Oh,
factual combination.
yes. So it has nothing to do with these guys.
Okay.
It's really a misnomer.
Okay.
Okay, so like I think these two things for both him and I, they live in different parts of our brains. So this has to do with operas, and this other guy we did the very as different as possible, which is for some reason we conflated the names.
Okay, so my second question is if that shape of local nature,
Which one?
the spectral comparison, so and in the consonant shape,
Oh, no, it's a what do you mean local?
yeah, I mean
Is there some local to global construction that produces it? Great question. We don't know. I don't know offhand. Great question. Maybe. Just we thought of it in global terms. So let me just say that
Like when you define the usual Poincaré sheet on the genetic side, so the way we defined on day one was using this bun and omega. And that was a global definition. But in fact, this is part of local to global Poincaré. So when we talk about this spectral Poincaré sheet, yes, in the sense of last night, we defined it by a global procedure. Maybe there's a local to global one, which just didn't occur to us.
Like morally, it's like someone instead of passing like a comfort potion of spa, it's like passing the awareness a little.
Say one time.
Like it's kind of
Well,
Come on, come.
not like fix the volume, but
It will see you. At least we'll see you.
yeah, okay, yeah.
This is good.
I'm definitely not writing anything. No, but just I think I'm saying the following stupid thing, which is just that right. Like the local picture, like you take the constant sheaf on this, like the action of SPA on it kind of factors through some quotient. And it's not just GFO equivariant, it's GFF equivariant. So there's some further localization. And there's some picture where kind of like the relationship. I'm not gonna say this well. The point is like, okay, it's like for people who know these words, like Koszul duality switches like equivariant type conditions and Whittaker type conditions. And like this flavor thing of constant sheaves and whatever on this side is like imposing more and more and more equivariance. And on the dual side, it's like when you look in the singular support directions, you're doing some sort of Whittaker flavored thing. And that's like this.
Yeah, but so the question was very precise.
Yes.
Can we write down
Yes. So,
those of the global functor who which this spectral functor is a particular case? That's the question. Like I wish we could.
yes, I don't literally have a precise answer to this question, but I think maybe it's just the stupid thing I'm saying is that there's a relevant quotient of SFA, which governs this type of thing. And like in SFA, you have some sort of factorization algebra, which is just the dualizing sheaf
Yes.
on this side. And on the other side, it's like equivariant slow to slice. And
That's
so,
true, but it's I don't know if it's or it's. But we don't know the answer to this question in short.
we don't literally know the answer, but I'm just saying like
There's a pathway to the answer.
there's a pathway to the answer. Yeah.
It was a great question to which we don't know the answer.
Yeah. But hey, it's like the confusion. Let me answer this. There's
So all the factorization techniques appears only on the market side, right?
No, I mean, see, like in this advantage diagram, we also have factorization, a lot of factorization going on. Just for this particular object, we don't know the answer.
but like yeah, it's kind of
And neither do we on the automorphic side. So here, there you want to produce a constant sheet. Like, can you make a constant sheet? So let's not bother about second side. You have a constant sheet. Can you produce a constant sheet as part of some local to global function? We don't really know, right?
yeah, but I think that I know the best way, but it's like also on the again, this stuff has to do with like somehow when you look at the principal closing orbit in same
Yeah,
on the spectral side.
yeah.
That's like really localized the thing you want. Yeah.
Anyway,
Okay.
no. Any more questions before lunch? Yes. Go ahead. Yes.
Can I ask a general question? So, would you say if you work about the neopotent inverse accord, and quantum parameters? Because, it seems like, due to the tempered version, it seems roughly every element parameter is already tempered. So which,
Yes, I can. Yes, okay. So that's a valid question. Okay, it'll take me 3 minutes. So we have precise conjectures on the connection between this and orthoparameters. So I can say what it is. Okay, Conrad, what kind of questions did you have?
One was also the GUI functions between Berger and Stanislau. So your answer was the favorite one and then one.
No, yes, yeah. So that's the same question as before. I'll address it with you. So what else? What's the second question? Okay, let me answer the Arthur question. So it's a kind of follow-up to GLC, but maybe it belongs rather to the this afternoon. So this has to do with. So this story implies GLC over function fields with elliptic sheaves, and so what you prove there is trace of the Frobenius on sheaves. Now we talk about elliptic sheaves when we focus single support on one sheet. So, okay, on the one hand, we know that this is the space of automorphic functions. So this is the back supported automorphic functions. The values from kilobar. So this is proved in this paper AG Kerr. But now, thanks to the geometric Lagrange, so this is equivalent to global sections of the dualizing sheaf, or what we call the stack of arithmetic local systems. And what No, maybe I don't even need to say it. Maybe I do need to say it. Sorry.
That's great.
I didn't want to say it, so let me say it. It's trace of Frobenius on int nil, as we've been discussing. Okay, so now this side has a filtration by nilpotent orbits. And so therefore, this filtration induces a filtration on the category on the right-hand side, and therefore it introduces a filtration on the trace. So we obtain a mysterious filtration on the space of functions with compact support indexed by nilpotent orbits in the Langlands-Dooley algebra. So that's what we've got. Yeah? Again, the logic is that equivalence of categories, therefore the trace of Frobenius are isomorphic. The category itself has a filtration by nilpotent orbits. Therefore, the category on the right-hand side has a filtration of nilpotent orbits. Therefore, when I take the trace of the Frobenius, it has a filtration. So here and now come the conjectures that can connect this to Arthur. So here's what we say. So, like it's a three-tiered conjecture. So conjecture one is that, so note that this vector space is defined over Q, and the filtration is defined a priori over Q bar. So filtration is defined over Q. Over Q. So the next part will be, so it's defined over Q, you can complexify it. So you can consider the induced filtration with complex valued functions. Your complex valued functions sit inside L2. So now Arthur predicts that L2 of Bungie over Q splits also as a direct sum indexed by nilpotent orbits where and the composition is determined by the Hecke eigenvalues. So basically what corresponds to the zero nilpotent orbit is the tempered part. So you look at the spectrum of the Hecke algebra, and so if your spectrum is tempered, you are zero nilpotent orbit, otherwise it predicts. I can say a few words about what exactly it means. So this is Arthur conjecture. It's proved only partially by Cardano and Cohen, dependently by Kevin and Wyatt. But so now here's what we're saying, that now, so the conjecture is that if you intersect, so if you take compactly supported functions on Bungie over Q and intersect it with the direct sum of terms below given nilpotent orbit, in terms of analytic decomposition, this will be exactly the term of the filtration here. It will be less or equal than O on Bungie of Q. So what it tells you that this filtration on here that we obtain by categorical federations, named this kind of singular support, nilpotent singular support, it translates into some analytic properties of Hecke eigenvalues. So that's part B of the conjecture, and part C of the conjecture is the following. So if you assume B, you obtain the following. You take the associated graded piece corresponding to given orbits, then we call it Gur O of functions with compact supports. Yeah.
The sum is over both.
Nilpotent orbits.
Yeah, but is
But I know zero is equal.
oh yeah, no, the price fixed.
yeah, the prime fictive. So according to B, this embeds into the piece of the arc or decomposition corresponding to O. So but now the part C of the conjecture says the following, that so the what we call it. So now I'll take the part here. Like supports that behave the part here that behaves Hecke-finitely. So just take the Hecke algebra continues to act, take just well Hecke-finite. So like vectors behave locally finitely with respect to Hecke algebra. Claim is that under this embedding, it maps isomorphically to the discrete part, discrete spectrum. This mysterious discrete series that they are of algebraic nature and they all complicate. So that's that's how it connects our projection. Does it answer your question? Yeah?
Can you repeat what superscript was?
Discrete. So like in L2 it's pardon me?
Like greater or?
Hecke finite. Yeah. Go ahead.
No, I'm just delighted we get this.
So you want?
You really think this is how you do this good too?
Yes.
Okay.
Conjectural. Have more questions, ask Kevin. Please. Make your response a little bit. Well,
Yes, so it's a question about something that was a few days ago. So we said that the vacuum model for the Django sleeping category can be made into a factorization algebra.
yes.
So how is that?
So here's what Gurbir's answer. And then I'll give my answer. And maybe there's some more answers. So Gurbir says the following. So you have the run space. And to run space, you can attach, there's a sheaf of Lie algebras in the run space, namely the arc algebras, right? Like at every point X, you take like G of O. And it factorizes in natural sense, right? Like the formal disk factorizes and we form the sheaf of algebras, G of O. Also, you have the sheaf of loop algebras, G of K, also factorizes. And the former is a sub in the latter. Take the induced module from the trivial module from the former to the latter. And that's your vacuum. So I'm saying that sheaf of Lie algebras factorizes, subsheaf of Lie algebras factorizes, hence the induction factorizes. That's Gurbir's answer, right?
Later.
All right. So now I'll give you my answer. You won't like it. Or maybe you will. We'll see. Oh, in Blackboard. Okay. So we've got the focus. So you have this G run. So, but there's more to it. It's a space, but in fact, it's a crystal. Well, I mean, everything's a crystal around. Round with the round. Didn't say anything. But it has a unit section. Trivial bundle with and take distributions, take the D module on it and push it forward. That's the vacuum representation. So take a D module, push it forward as an int-coherent sheet.
Which
The delta function of the unit section. But push it forward as an int-coherent sheet. So forget the D module structure in the vertical direction and push it forward. And that's the vacuum. That's another way to look at it. And again, no surprise because I find this line is acted on. So if the loop group, the stabilizer of the point is exactly this arc group. So in any situation with the vector space underlying the delta function is really an representation. But this is a more geometric way to think about it. Any other ways to think about this?
I just want to say like historical origin of the thing was like people talk about vertex algebras instead. You can go and open Frankel's book to actually see what this thing looks like. State operator corresponds.
But also mentioned about Frankel's book is called.
Yeah. Vertex algebra is not very close.
No, there's an answer.
Yeah, something to think about it.
Yeah. All right.
But actually, so, for the earlier question, I now think there's a reasonably precise answer, which you just take just instead of working at critical level, work at level 0.
Yeah.
Look at just integrable representations. There's just the fact, there's the integrable quotient, aka the trivial vertex operator algebra.
Yes.
Take twisted, the one point is to take twisted conformal blocks in the intelligent way to send the Bun-G.
Oh, the previous question.
Yeah.
Indeed.
Yeah.
Okay. Okay. Well, so he's answering your question. We'll what's the question? The speculative Poincare sheaf, like the guy that corresponds to constant sheaf on Bun-G, is there a local Gaudier procedure that produced within either side? And Gaudier is saying yes. Well, let's discuss it over lunch and then there's an answer.
Yeah.
Any more questions? I heard another question. Yes, go ahead.
In case G is semi-simple, can I also use that utilization with credits and feedback cosmologies to understand that I have spectral action?
Say one more time.
If G is semi-simple, can I
Yeah.
use uniformization of Bun-G to see that I get spectral action?
Spectral action like Lynn was explaining yesterday?
Yes.
No. Not really. That doesn't help.
You can just take one point because we're talking about like 80.
No, so like let me say it like this, the only way we know how to prove spectral action is using localization to critical level. Like for example, we don't know how to prove it at other rational levels. So we are supposed to have spectral action, and there is no critical localization. There is no this mysterious, this amazing Berti-Volkers property, like this Hecke property, eigenproperty, local level. And because we don't have that, we don't know, we don't have the conjecture spectral competition, but we don't know how to prove it at rational level. So the only currently available way is continued localization. We cannot do it with pure geometry, unfortunately, although the statement is geometric. Statement geometric, we can't prove it. More questions?
A and B imply LG10 conservative or constant.
How does it apply?
Yeah, because
Yeah, let me do it. What is your opinion? Your responsibility.
What was the question?
Why A and B applies if L10 is
So one line.
okay. You'll be better going with that.
Lunch.
Okay, really should be. So again, so after this question, lunch.
Okay. So theorem A. Now I've kind of forgot what. Anybody remember what theorem is?
the kernel of the.
Ah, yes,
But it's the close, not L10.
yes,
Theorem A was like the current kernel of course.
yes. We'll prove that the kernel was D modules with irregular nilpotent singular topology. And theorem B was that there are no nilpotent tempered nilpotent D modules that have nilpotent irregular singular support. Okay, that was theorem B, which we haven't really addressed.
Zero equals 0.
Equals 0. And let's remember what the goal was. The goal was to prove that if you have F nilpotent D module
Yeah.
such that LG force of F is 0, then F is 0.
Remember you write LG10, not LG4.
It's the same. Temp. It's the same. Course evaluated on the tempered category is temp.
And to commute that fast, okay, so about the community diagram. We have T1G10. Sits inside T1Q. We have LG horse. We can go. Check, and by definition, this composite was called LG10.
So let's write it in a bigger diagram. So in reality, we have d bun g going by means of the Lagrange functor to int code. So inside here you have d bun g temp, and here you have quasi curl. And so here is this, let's call it the temper functor. Now there is an embedding, and it's left adjoint, right. Embedding right adjoint, embedding right adjoint, and both circuits commute. It commutes this way or commutes this way. But and what we call the LG course is this. LG course can be thought of, take LG and apply the right adjoint from int code to quasi code, or coarsen to temp and apply this functor. But again, everything commutes. So LG course evaluated on temp is temp, however you think about it. Does it answer your question?
And then the intersection is zero, how does it apply?
So take an object here, assume it's zero. Their A implies it lies in here. So it lies in the intersection, which is zero.
All right, let's have lunch.